Hey, any questions? Yes.
Go over number 15, 16 on the practice again.
For which chapter?
For 4.
Why don't we go through chapter 4 some before we do this? Other questions? No? No other questions? Okay. Sorry. Not right now. Good answer. Okay, so a couple people were asking some questions up here, which are general interest questions. So specifically for exam number 2, we will be allowing the use of non-working calculators. You don't have to use calculators for the exam to get all the questions right, but if you want to bring one in, you can, as long as it's non-graphic. Phones will not be allowed.
Is it recommended to bring a calculator, in your opinion? All right.
Yeah.
I mean, like the computations, like they're not gnarly or anything, right?
No, there's no gnarly computations. As a matter of fact, everything in that exam, you, as a senior,
Okay, so
PS
you-
program or graduate student, should be able to do all of these problems without any aids whatsoever.
Theoretically.
No, not theoretically, very practically. Very practically.
Someone said they're math.
If you know logs base 2, you got it.
Yeah.
I know what log base two.
If you know how to count, you're good. If you know what a megabyte is, a gigabyte is, how to do math, that kind of math.
Oh, okay, I guess 10 to 20.
Yeah.
Okay, all right.
That's why I said logs, right?
Gotcha, yeah.
Simple log math. Okay,
Oh, well,
yeah.
sorry,
That's
same
okay.
structure as last time for the exam?
Yeah, the exam will be the same format structure.
About 8 to 10 questions, probably around.
Roughly the same number,
Okay.
some subdivided like we did last time. There'll be very different questions because of chapter 3 and 4, of course. Other questions? Of course, you nailed 3, right? Because we've completed 3. We're just going to go through 4. You've done the readings on 4 over the weekend, I'm pretty sure, because we have some questions here already. And so what we're going to do now is we're going to go through some of our prepared stuff, but really it's to sort of reinforce and answer questions you had from your readings, or maybe untangle some confusion you had from the readings, right? I'll say, yeah, sure. Somebody did. Somebody must have. Okay. That way, in, getting out. Here we go. Chapter 4. I gotta remember this sequence, is it? Control L? Supposed to be Control L. I'm gonna try not to. All right, so file systems. What did we just finish up? Chapter 3.
Chapter 3. Paging, segmentation, stuff like that.
Yeah,
Memory management.
okay.
Replacement.
And chapter 2, well, we already did 2 previous examples. Okay, so you got that. Now for chapter 4, we're going to start looking at the file system. So it took us a couple of chapters to talk about the virtual processor, right?
Yes.
The file system is going to be a little bit more succinct. We can pretty much contain it in one chapter by itself, but really the file system and the I/O subsystem, which will be the next chapter, they do have a lot of dependencies upon each other, but they're still very clear by themselves that we can talk about them quite clearly, okay? So the file system, the idea with this is it's a method for us, or more than a method, it's a mechanism for us to be able to manage memory. Long-term memory, short-term memory, right? It's a way for us to manage memory. We have processes, we have files. And so that's the purpose of the file system. We're gonna create all these mechanisms for us to be able to manage memory, okay? And there's some ways to say it just exactly that. So, just like we came up with a notional mapping of main memory, which fortunately nobody chuckled at me when we showed how we came up with this memory construct for management. Likewise, we're going to come up with a virtual representation of all the addresses on our long-term storage. And we're going to make them kind of look like this. So we have address 0, 1, 2, 3, so on to n minus 1. Addresses for this. Now this is, again, a construct that we can work with in our heads so we can come up with some tools to manage this by looking at the notional representation of those addresses like this, okay? So, the other thing we need to think about with these systems here is that we probably don't want to address every single byte in this thing, do we? No. What kind of transfers do we do?
We do block transfers.
We do block transfers. So I want a block, right? If I don't want to address every single byte in here, which I don't, then what I want is a block. So what I really want to do is come up with a scheme where I can manage this address spaces divided up by blocks. So I'm going to take this whole thing, create a file system for it, and this file system is going to create addressable blocks of memory chunks, okay? So we're going to come up with a scheme that helps us do that. So that's one thing we are going to do kind of right away, right out of the box here as we start thinking about file system construct. The other thing that we want to do is we need to have a way for us to be able to find stuff in here. It's really no good for us to keep dumping stuff into this file system here if I can't ever get anything out of it, if I can't ever find anything to get out of it, right? Kind of defeats the purpose, right? Except for just pure archiving. So I need to be able to search through here, find something specific that I want, either by specific address or content or a file name, or, and once I've done that, then be able to get data out of here. Okay? I'm also going to need to provide protection mechanisms, right? So only those users that I want to have access to any one block can have access to any one block. So I want to protect each of these blocks, but I also want to be able to let some of these blocks share amongst multiple processes, multiple users. Okay, so when I'm thinking about my file system organization, I'm going to keep those things in mind because those are some hard requirements that I need to think of as I design this file system. When I say I, it's all of us, right? It's the global we. All right, so immediately when we start talking about file systems, everybody immediately goes to file names. It's just a natural thing. Okay, so let's go ahead and get that beast taken care of right out at the beginning here. Okay, file names typically have this kind of naming convention, where you have a name, a dot, and a file name extension. Some operating systems, like Unix and Linux, really don't care about file name extensions. They just don't care. The compilers do, some of the other tools do, but the operating system itself doesn't care. Whereas some operating systems, like Windows, forces you to have file name extensions, whether you want them or not. Okay, so you might like that, you might not like that. That's just the way those particular manufacturing lines went. So given that they are widely used, we have, as an industry, sort of standardized on some file name extensions, and I think everybody in here is more than familiar with these and others, right? But you should be aware that not all operating systems require them. Okay. Having said that, we got the file name thing out of the way. There's also some really interesting ways that we store these file names. So we sort of foreshadow that a little bit. Can I hit the pause button for just a second? There was one thing I didn't mention last lecture that I did put into your study guide notes that I want to make sure that you are aware of. Okay? I know it's in the study guide notes, so I know you're aware of it. there are, in order for us to implement paged memory systems, there is a special piece of hardware that that particular system is required to have. And it's called a PMMU, or a paged memory management unit. Some will just call it just an MMU, some will call it other things, but typically they're PMMUs. Okay, that's some hardware that's dedicated hardware that's required in the motherboard to be able to support paging systems. This device here in the chip is going to do the address translation between the virtual and the physical addresses based upon that particular manufacturer's architecture, right? So the number of bits or bytes rather that are used, bits that are available for use for the page number versus the offset number, that's all going to be determined in the PMMU. And so it can do all of that address translation that we saw in those graphics that on the chapter 3 slides that we were talking to. Okay, so that is required. It was never required before. You can implement all of this in software, and there were a couple systems that did, some earlier Pentiums, they did that, but they kind of went away from that. Everybody was required to use this. There's a question over here?
Oh, what is it exactly? What's required of PMMU or in the motherboard?
Yes. That's what, if you're gonna provide, if you're gonna perform paged memory management, if you're gonna perform paged memory systems, not, so if you wanted a segmented only system, you still don't need one. If you're gonna use paged memory, or if you're gonna use page segmented memory, you are required to have one of these.
Oh,
Okay? And more recently, we're now seeing these chips being part of the chipsets. Whereas the input-output main memory management unit, which does the same type of thing, but is dedicated to the I/O subsystem, which we're going to study in more detail here a little bit later. Okay, so the I/O subsystems more recently have one of these, so we don't say it's required. I'm just making you aware of that. This is required. This right now is optional. Yes,
Where's the PMU located? Was like part of the memory controller or actually in the CPU?
it's on the memory controller. It's on the board itself.
Okay, well, because like I know like newer CPUs are integrating the memory
Yeah.
controller into the CPU, so it's like shorter distance.
Yeah, well, newer ones they are integrated.
Yeah, well, they're not completely integrated, yeah. And then I think some of them are even like, aren't they integrated in the I/O controller now too? Some of them?
Yeah, yeah, I think there's a lot of these are starting to show up inside the I/O processor. Okay. Important digression. It's in your study guide, but I thought I'd better point it out. All right. Where were we here? Oh, yeah. Naming convention, we talked about that. So now we're talking about looking at how we're going to organize the file systems. Okay. One of the things that we do is we do this in this direct correlation of database lingo versus how we're going to organize this thing called file, right? Because there is a direct correlation. What are the different parts of the database storage system? Come on, that's me. You've had the database class.
Wait, what was the question again?
So, what are the different parts of a database storage system?
Like the engine? Are you talking about?
No, not the engine itself, but when you're trying to create something in a database, it's organized into
Tables, rows, columns,
fields.
yeah, fields, and rows.
Rows and columns is a way to organize fields and records,
Yeah.
right? So you have individual fields. You then have a collection of fields inside of a single record, which would be a row. And then you have a table,
You have views too.
which is, these are something that you would use to view, this is what you're managing the data with. And then a collection of records is a table. Okay, so the same thing applies with our file system, where our file system can be viewed as containing fields, records, and tables, where a record might be files, fields are individual bytes inside of the file, and then the table is this collection of records or files themselves, which is our file system. Okay, so there's an analogy there, and when we started talking about some construct techniques, this wasn't too far from our thinking when we started coming up with some of these organizational techniques. Okay? So one way we could do this is we could just, like I was saying earlier, we could do byte addressable, which is the byte sequence representation, or we could do a record sequence where you have a record or a file, you have a collection of records making the file system. Okay, you can organize it that way, and if you do it with byte sequencing, then you are literally going to every single byte individually directly, right? Whereas if you do a record sequence, okay, you could do offsets by blocks or files, if you will. But that's still doing sort of this offset thing. And what's more helpful for us is to be able to go as direct, as quickly as we can to the first byte, or block rather, of our file. And so this tree organizational structure is the way we organize most of our file systems today, where I'll have a collection of records or top-level files that may have some pointers to some other files, which may be an actual data file or maybe another directory file, in this case here a directory file, to yet another sub folder or sub file, okay? So this tree structure is the way most of our file systems are made today. Various systems use those other techniques, byte sequence, record sequence, but we quickly evolved into this tree structure, which allows us a great deal of flexibility and the ability to quickly get to any file that we need to. Yes?
So I don't know, when I first looked at that, it was kind of misleading, because it looks like it's saying that cat, cow, and dog is in between and fox, as opposed to something there. It's supposed to be in a hierarchical structure, so.
Oh, so one of the things that you see here, at least I think we do, right? Okay, let's back up first to your question. Your question was, this was misleading because you thought.
Yeah, because you described it as being hierarchical, there
Yes.
I'm reading that as, that's just saying that's what's in between and fox, as it's one linear record, and it's just breaking it up for some weird reason, I don't know.
Oh, no, so the way this works is that since it is hierarchical, which is correct, these are all at the same level, right? And the fact that I have even lower level ones, third level in this case here, means that from the top level, I have to first go to one of the lower levels before I can get to here.
So just seeing something from up there is pointing to that second level, not that that's here.
Right, the fact that this one doesn't have a third level doesn't make it any less or more, it's still hierarchical. And at some point, you might add another file, which is a directory pointer to a third level. What that means is that in order for you to get to this file here, you're having to start off at the top level, kind of getting ahead of ourselves, but since you brought it up, you have to start off at the top level, navigate, in this case here, to goat, before you can navigate to hen. So in order for me to get to hen, ibis, or lamb, I need to start off at my root level, ant, fox, pig, and go to goat, lion, owl, to get down to here. I have to do those dereferences in the hierarchical system. I have to start off here in order to get the pony, rat, worm, or cat, cow, dog. Yeah.
When you go to the next time, what were you mentioning about the bits, records?
What I was saying here is that with the byte addressable, okay, I'm gonna spend a lot of memory and processing getting to address every single byte in this very large file storage system. Okay, so I can go directly to any byte, but I'm gonna have to form very long addresses and probably some complex addressing mechanisms to get to any one byte. And it doesn't do me any good, because every time I do a transfer from my main computer to the file system or the other direction, I'm gonna do a whole block transfer anyway. So I'm wasting a lot of resources doing byte addressable, not good. Record addressable, I could do it that way, but then I've got some complex ways of trying to organize all of the files. And we're gonna take a look at some alternative ways to do that too, in a little bit, some more slides. Okay, other questions? HFS? Okay, as a reminder, because we did this in chapter 1, right? We have these 6 file types. Okay? They all, each of these different file types have their own organization of what each block looks like. Okay, so they're all gonna have the same size blocks. Every file type will have the same size block, but they're gonna be organized differently because the purpose of each of these files is different. Make sense? Now the regular file type, it's easy to kind of get confused about what a regular file type is because a regular file type will be executables in libraries in addition to text files or files that have a special format for any of those other types of files, in the sense that you have these file name extensions that says I'm an MPG, therefore it's formatted so that programs that understand MPGs can understand it. However, when we go to use the internals of the block, it's going to be organized the same way as every other regular file type. That's an important distinction. So I say file type in a file system, it's one of these 6. If we say file type based upon naming extensions, that's an application level discussion. Got the difference there? Okay. So these 6. So let's look at the first one, the regular file type. Probably the more complex, certainly the most commonly used, but they're all important, okay? File type, a regular file type looks like this. You're going to have some bytes organized to contain header information about this file. Okay, and you can see some examples there. And what's important about this header information is based upon the way you construct your loaders and the way you construct your processes that are going to be opening, closing, and otherwise manipulating files. They're going to need to know things like which of the 6 file types this is this, how large is this file, where's the symbol table, all those different kinds of things, where's the data size, where's the different regions of it. And then you get to the actual file itself, the text, data, relocation bits, and symbol table, and so on. Okay? That's how you would organize it for an executable file. Okay? As an archive, what you're concerned with is you're concerned with the header, which is going to have module name, owner, protection, all that kind of stuff. Modules, object module, header, object module, because an archive file is going to be this collection of executables. If you're not familiar with working the insides of an archive file, you should go and take a look at it. You have some tools that you can use to go and look at the contents of your math.o or SO or SA, not the SO so much, but the .a, .essays. You can go in and look at each of the different compiled organizations of modules that are inside of each one of those archives. Okay, so that's why you're going to organize the contents of an executable versus the contents of an archive and the contents of whatever other type of file you're going to have. They're going to have their own organization of the data that's inside of the file. Now that's not the file organization itself, that's how you're going to organize what's inside of the file. Is this stuff here telling you what you need in order to load up an executable file, right? Because you know the data region and text region, we talked about that, and as well as the BSS. So there's your 3 areas right there, and of course the stack. The stack's going to be blanket first, yeah?
Ouch, we always BSS, the acronym sample.
Everybody remember? BSS? Statics.
Statics.
Yeah. Okay, so some of the attributes now for the file itself. This isn't necessarily a complete exhaustive set for any one particular OS. These are what you'll normally find in every operating system. Some operating systems will require more. But they're going to have things like who owns this file, who created the file? Is there any, what are the protection bits on this file? Right now, everybody's familiar with the way Unix and Linux do it, right? Where you have X, WX, for
The owner, user, and group.
owner, user, group.
Confidence left and right over.
That's right, yeah. Well, it's a owner group user.
Owner, group, user.
Yeah. It's OGU.
Yes, it is, OGU. I was following him, actually. Start up with the owner, next level up is the group,
User.
next level up is user. No.
Yes, it is. That's right.
That's not owner,
What is it?
that's other. It's like world, it used to be called W for world.
Oh, that's right. Well, yeah, I guess it's a person that created the file, then the group, and then everybody is what it is. I don't know the.
Read, write,
separation.
execute, it's the other way around. Starts off with the user,
Yeah.
then the group, and then W/O. Some systems are W, some are O, world or other.
It's mostly.
Read, write, execute, read, write, execute, read, write, execute, so you really don't want to do that, right?
No, never, basically.
Except for maybe, yeah, you never, you never want to do that, right? Because then you set all the bits for everything, and that's usually not good.
Usually it's 7.5.
For executables, yeah. The executable library sitting around there. And of course, in your student accounts, right? I don't care what this is, but those are always zeros, right? Okay. So protection bits, everybody has them. And then there's all of these other flags, which are kind of important, otherwise we wouldn't have them, right? They all have their very specific purposes. And this is, a typical set. Some operating systems like this will have more or less. And then we have this collection of system calls that are available